So in this video, my aim is to give you a visual interpretation of what this integral, this new type of integral, is calculating. Okay, so kind of, can we predict what the output, what the result of this integral is going to be by knowing what the curve is and what the force or what the field F is? Can we predict the result in some way? And the way we're going to do that is with these plots here, but before I show you the plots, let me define what I'm going to do. So the integral over the curve C of f vector dot dr vector, if we substitute dr vector as being equal to dl times a unit vector t hat, because the norm of dr is equal to dl, right? While the direction of dr is the direction tangent to the curve. So this t hat vector is a unit vector tangent to the curve, okay? So if we do this substitution here, our integral is actually doing f dot t hat times dl. And if we kind of write a parenthesis here, this is nice because now this dot product will be a scalar function which we could call f, little f, okay? So now what we are doing is we are doing an integral of little f dl. So we are doing a normal line integral, okay? So this is like when we were calculating the mass of a wire, we just substituted here the density of the wire at each point, and this would give us the mass of the wire, right? So that was easy to see intuitively. So now what I'm saying is that we can convert one of these integrals into one of these other integrals by simply saying that this scalar f, so the mass density of the wire, is simply the vector field f dot t hat, the tangent to the curve, okay? So what I'm going to do here is plot exactly that, okay? So I'm going to plot this little f. Actually, let me modify this. So I'm going to plot f dot t hat, okay, which is equal to our scalar f. And since this is a scalar, it is a value, a real value that goes with, it can be either a negative number, a positive number, or it can be 0. So I'm going to color code this. So it will be red if it's negative, green if it's positive, and black if it's 0, okay? And I'm going to show you different examples. So in these examples, the big circle here in the center is the path of the integration, okay? That's the path, the curve C. While the small arrows that are surrounding this, so the small arrows that are defined everywhere, that's the field f, okay? So that's a field defined at every point in space, okay? And this integral here, if you remember, would be the work done by this force going over the path C, okay? So imagine that we have a force that is pushing a mass always in this direction, the azimuthal direction, and we choose this path, which is a circle. So the integral f dot dr will be equal to the work done after traversing this path, okay? But at the same time, we are going to reinterpret this as the mass of a wire in which the density of the wire at each point is the dot product between the vector field f and the tangent to the curve t hat, okay? So for example, here, if you choose any point along the curve, the tangent to the curve at this point is obviously a horizontal vector, t hat, while the force is also horizontal when you are at this point, right? So then f dot t hat is going to be a positive number. So that's why it's painted green. And actually it's going to be a positive number everywhere, so that's why this line is green everywhere, okay? So we are going to get a net positive result when we do the integral. However, consider this other case. In this other case, we could say that this function, this could be gravity, for example, okay, the force of gravity pointing downwards. And now we are moving a mass over a certain circle, a closed loop. Yeah. So at each point we can define, for example, when we are here, we can define our tangent unit vector t hat as horizontal, while our force is vertical. And therefore f dot t hat is going to be 0, and that is why I painted at that location, I painted the circle as black. Okay. The same thing happens here when the tangent vector points to the left and the force points down. So the dot product is 0. Now on this region, the tangent vector is pointing kind of upwards, while the force is pointing downwards, right? And therefore the dot product f dot t hat is going to be negative in this region. It's actually going to be more negative here, and then less negative, less negative, less negative, until it goes to 0 here. So that's why there is a gradient between red and black. While on the other side, the opposite happens. We have that the tangent to the curve is kind of pointing downwards at every point, and the force is also pointing downwards. So therefore f dot t hat is positive. Okay. So we have a very positive value here, and it gradually decreases until it reaches 0 here. Okay. So therefore, when you integrate the total work done, you are going to get positive values here, negative values here, but everything is symmetric, so the final result will be 0, right? And this makes sense if you think about the work done by gravity on a closed loop. You know that the work done is 0. But you can also reinterpret it as the mass of a wire, where the density of that wire is this color, so you have positive mass density on the right, and negative mass density, so this would be negative kilograms on the left. I know that's impossible in physics, but maybe this was, instead of mass density, it could be charge density, and you can have negative charge. So this is positive charge density, negative charge density, so the total charge when you integrate, using this interpretation, it would be 0, okay? So it's kind of fun to see that you can work in the world of work done, or in the world of calculate the total charge of a wire. And they are, mathematically, they are equivalent, okay? Let's see more examples. So the fields are the same, but now our path is this triangle. So here, while we are moving down, f dot t hat is positive. In fact, it's more positive here than here. Why is that? Because t hat is always pointing down. But the force, the angle of the force is changing, so that the angle is 0 when we are exactly here. So the integrand f dot t hat is maximum, it's positive and maximum, and it's slightly less positive here because there is a certain angle between the force and t hat. There is a certain angle there. But it's still an angle less than 90 degrees, and therefore it's still a positive value. So that's why we get green. Here it's a lighter green. Sorry, here it's lighter green, indicating more positive, and this is darker green, indicating a little less positive, but still positive. Okay. While in this section of the triangle, this is interesting because the force is always pointing there or there, right? While the tangent to the curve is pointing in this direction. So they are always at 90 degrees, so we are always getting 0 for the integrand f dot t hat. So this section of the path will not count towards the integral, okay? In this example, we have the force of gravity and we have this triangular path. So along this path, f and the direction of travel are perfectly oriented. So we get a maximum, we get a positive value, which is also constant. So f dot t hat is positive and constant. So it's light green. Then here we're moving up at a certain angle. Yeah. So this is the function t hat, while the vector f is pointing down. So the dot product is going to be negative. Not going to be completely negative because they are not opposite to one another, but they are at a certain angle that is bigger than 90 degrees. Yeah. So the angle between the two is bigger than 90 degrees. So it's going to be a negative number, but a bit darker. That's why this is not bright red, it's dark red. And then in this top section here, the tangent to the curve is horizontal because we are moving horizontally, while the force is pointing down, so the work done is 0. Yeah, but you can also see that F dot T hat is 0 throughout the entire leg of this triangle. So that's why this is a black section. Okay? So I hope now you are kind of developing this intuition. So finally, I can draw here like a random path on these two fields, and you can see how the integral will look like. So here the integral will be very positive, here it will be positive but less positive, here more positive, less positive, more positive, here it will be 0, then it becomes a bit negative, then 0, then a bit negative, then very negative, and so on. Okay, so the meaning of this path integral will simply be the addition of all those positive or negative parts. Okay, so in this case, since everything kind of is symmetric, you will get also 0 because this is a closed path and the vector field F is constant, pointing down. So this would be a 0 integration. Okay, while in this case it would be a net positive because you are kind of moving in the same direction as the force. So the work done will be positive, the net work done. Okay? One final lesson to take away is that the direction of the path is important. In fact, if we swap the direction going in the other sense, going in this sense, the sign of the work done or the sign of this integral would change, okay? Which means that if we're calculating the integral of f dot dr on some curve C defined in this direction, this will be equal to the minus integral of f dot dr of a curve that we could call the curve minus C, which would be an identical curve, but moving in the other direction. Okay, we could call this curve minus C. So if you change the direction of integration, you change the sign of the total integral. Okay? And this is because there is a dot product. So the dot product does care about which direction are we moving in. Okay? This is different to the normal integrals. So let me write it, different to normal line integrals. For example, if you are calculating the mass of a wire, you can integrate the wire in one direction, or you can integrate it in the opposite direction. It doesn't matter. The wire is the same wire with the same mass. Yeah. So for normal line integrals, the direction of the path does not matter. But for these line integrals that have a dot product, the direction of the path does matter and actually changes the sign of your result. Okay? Excellent. Thank you very much. See you in the next video.